In this video, I will state the first law of thermodynamics, and I will go ahead and explain the sign convention associated with the first law of thermodynamics coming up. Before I get to the first law of thermodynamics, I would like to define what thermodynamics is. Thermodynamics is the study of the description of processes where heat supplied to a gas and work done by the gas are related. Or maybe I may simply say that thermodynamics is simply the study of the relationship that exists between heat and other forms of energy. Now, what is the first law of thermodynamics? Now, allow me begin this way. In general, the first law of thermodynamics here, we are trying to relate the principle of conservation of energy to how heat supplied into a system relates to the internal energy and work done. Now, by a system, I mean a gas. This right here is a pot. Let's assume inside this pot we have a gas. Of course, a gas has got those kinds of molecules. Now, when we administer heat into this gas, the relationship that exists between this heat being administered to this gas and the effect that follows as a consequence of this heat being delivered to this gas, the consequence here being the work done by this gas, is what we are calling the first law of thermodynamics. And in a way, you see that we are having this heat being converted into this gas, being taken up by this gas. And the relationship here has something to do with conservation of energy. Now, the flow of conservation of energy, if you may already know, states that energy is neither created nor destroyed, but it can be transformed from one form to another. So when it comes to the first law of thermodynamics, this is exactly what we are trying to illustrate. This is heat. This heat is heating up the gases, these particles inside this. Now, of course, we know that these particles in between here have got what we call intermolecular forces of attraction. These intermolecular forces of attraction between these molecules in this pot of this gas are what are giving us the measure of the potential energy in these particles. Of course, if the intermolecular forces of attraction are weak, it means that these molecules will be far apart. When the intermolecular forces of attraction are strong, these molecules will be close enough. Now, these molecules, because it's a gas, they are always constantly moving and hitting the walls of this pot. And because they are constantly moving and hitting the walls of this pot, they do so by some velocity. So this velocity of these particles gives us the measure of the kinetic energy. So when we look at a system like this one, we are seeing that these molecules have what we call both potential energy and kinetic energy. Now, when we add the potential energy to the kinetic energy, or if I may say, the summation of the potential energy and the kinetic energy is what is giving us what we call the internal energy of this gas. So in other words, the internal energy of this gas is simply the summation of the potential energy and the kinetic energy of the particles of this gas. So we shall be referring to the internal energy of this gas, or we may call it the system. Now, when I say system, I mean this. The gas itself is what we're calling the system. Now, when I use the word system, it is just semantics. It is the kind of language we use in thermodynamics. Now, in thermodynamics, of course, the convention that we shall be using from now on to refer to this gas is what we are calling the system. If I may diagrammatically illustrate what I'm talking about, this is what I mean. Right here is a gas trapped into a container, and that's the piston. So the gas is what we shall be referring to as a system. So if the gas is what is the system, so what is outside? Outside it is what we are calling the surrounding. Whatever is surrounding the gas, that's what we are calling the surrounding. Now the system and the surrounding are separated by a wall or a boundary, and as such, both the system and the surrounding comprise of what we call the universe. So if I subject this system to heat, there is definitely going to be some change in internal energy of the system, because when we get this heat inside here, this heat is going to be picked up by these molecules. When these molecules are picked up, of course, the intermolecular forces of attraction here will weaken. These molecules will get more excited. So overall, there's going to be a certain change in internal energy. The internal energy here will either increase or decrease. Now, after this internal energy has changed, either work will be done on the system or work will be done by the system. What do I mean by those two statements? If I may use this container that is having this kind of piston, if I provide heat here, for example, and there's some change in internal energy, let's say this gas expands. If this gas is to expand and it is to push this piston upwards, if this piston is to be pushed upwards, it means that it is the system that is doing work on the surrounding. It is pushing back the surrounding. So that is what I mean by the system doing work on the surrounding. But it can happen the other way around. You may find that this piston is being pushed inwards. If this piston is being pushed inwards in such a way that the gas here is being compressed, it means that now it is the surrounding that is doing work on the system. So by saying these two things, I'm trying to state the equation of the first law of thermodynamics. Now, before I state the equation and therefore the law, please take note that there are many versions of this equation out there. If you're quite a reader, you'll soon discover that different textbooks will give other versions of the equation for the first law of thermodynamics. This may mean to confuse you, but it doesn't have to confuse you. Here is why. Now, each version of the equation has its merits, and the versions will be self-explanatory, self-consistent, and understandable. Only and only if you read and understand the definition of each term used in the equation. Now, at the end of the day, of course, upon understanding the meaning of each term in the context of the equation, it will all settle down to one universal fact, and that is that the equation is stating the conservation of energy. Like we said, the first law of thermodynamics is simply trying to relate the conservation of energy in the context that when heat is given in, it is converted into other forms of energy. So for this session, I prefer using the version below. This is the kind of version that is preferred by IB and UNEP, and this version states that the heat energy that is supplied into a system is equivalent to the change or to the equivalent to the increase in the internal energy of that system and the work done by the system. Now I hope you are taking note of the language here. I said that heat supplied to the system is equal to the increase in internal energy of the system plus the work done by the system on its surroundings. Ladies and gentlemen, this is the first law of thermodynamics. Now allow me to discuss the sign convention in this equation. If you realize in our equation, when we were stating the equation, all these terms are positive. This is positive Q, this is positive change in energy, positive internal energy, meaning that it's an increase, then this is positive work done. And this sign conventions being positive, it's completely different when all these sign conventions are negative. Let's take a good look at this diagram and look at the blue. This is what we just stated when we said that the heat energy supplied to the system is equal to the increase in internal energy plus the work done by the system. Of course, here, this first equation simply means, if I may interpret it in regards to this diagram, that if I supply heat into this system, supplying heat means it's going to change the internal energy of this system because the particles are going to gain kinetic energy and so forth. So this gas will expand and then it will push this piston up. When it pushes this piston up, it means that the system is doing work on the surrounding. When the system does work on the surrounding, that is why we're having positive W up. So you see all these arrows are pointing up, and that's the convention in this context. So it means that when heat is flowing into the system, it's a positive Q. And when the system is doing work on the surrounding, or the system is doing work, it is a positive W. Now, if all these were now negative, negative Q, negative change, or that is a decrease in energy and then a decrease in work done, it means now, let's say the piston is being pushed down. When the piston is being pushed down, it means that you're compressing this gas. When you're compressing this gas, that is negative Q, negative W. it means that some heat is going to escape out of this system. When the heat escapes out of this system, it gives us negative Q. It means it's going to be equal to a decrease in the internal energy and work done on the system by the surrounding. So this is a simplified sign convention that when all arrows are pointing up, they are all positive, and when all arrows are pointing down, it's negative. So if I may make a recap, in this video we said that the first law of the thermodynamics tries to relate the principle of conservation of energy to how heat supply to a system relates to the internal energy and the work done. And so following that statement, it means that the heat supply to the system is equal to the increase in internal energy of the system plus the work done by the system on its surroundings. We discussed the sign convention, and now we conclude. Positive Q means energy transferred from the surrounding to the system because the surroundings are at a higher temperature than the system. A positive U represents an increase in internal energy of the system. A positive W means it is work done by the system as it expands and pushes back the surroundings. Now, when each of these terms are negative, a negative Q simply means energy transferred from the system to the surrounding. A negative U simply means that there is a decrease in internal energy, and a negative W means work done on the system as the surrounding compresses it. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel, and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.